sorry I have to cancel at the last minute. I'm fine, I just had a really bad headache. And I was like, I don't even think I can stand up in my class. But I was better later. It's just like sinus stuff. I don't know. Nothing contagious. So we started talking about this idea of wholemeal programming, right? So organizing our programs in terms of putting together a pipeline of functions that kind of incrementally transform our, an input into the desired output, rather than, say, writing an explicitly recursive function ourselves, or going through things item by item. So this was an example that we did. And this kind of thing, like this isn't just fun academic exercise. Like people really write code this way, in production systems, because it's easier to write, it's easier to understand what's going on. Maybe when you're first looking at things like this, it might seem harder to read, but once you get familiar with all these different kind of standard functions and stuff, you can just look at that and be like, oh yeah, it's filtering, it's mapping, it's doing that. Whereas if it was written with explicit recursion, even though it's kind of more explicit about what it's doing, you have to think harder to figure out what's going on. I'll do a few more examples, and I want to first look at a couple more standard libraries that are often useful. I mean, there's lots, but so in the containers package, there's a lot of modules here, but we're going to look at two in particular. One of them you've already seen, I think. But let's look at Data.Set first. So Data.Set is just a set of elements, right? So an unordered, it's when we don't care about the order, right? It's actually stored, so it doesn't use a hash table. So in, say, Java, the way that you would represent a set would be using like a hash set would be typical. And it's using a hash table. The thing is that actually hash tables are kind of inherently mutable structures. So in order to insert something into a hash table, you have an array and you have to like modify a place in the array. That's kind of just how it works. And so that is less suitable for a language like Haskell. It can be done. There are ways to have mutable stuff in Haskell, but it's kind of not as nice. So they're like, it does exist, and if you really need it to be super fast, or you have an application where a hash table is exactly what you really need, then you can do it. But what's provided by default is, so this is actually implemented using a balanced binary tree kind of thing. It's not, it might not even be literally a binary tree, but it's some kind of balanced tree structure. So looking things up in a set actually takes log time, not constant time. But it's very, very optimized, and so it's pretty fast. And for all but, like, if you have like some giant data set, you're going to notice the difference. But for most normal things, it's very fast, you're not going to notice. So, yeah, size balance, okay, there are binary trees. So I'm not going to look through everything, but it's got things like you can make an empty set, singleton set, you can convert a list into a set. This only works for things that are ordered, because for types that are ordered, because it's like a binary search tree kind of thing. It's putting them items are stored in order in a set. Well, I love power. I didn't know it had a power set. That's new. You can insert, you can delete, right? A bunch of stuff. Lookups, union, Cartesian product. I mean, there's like take, split, map. But you just have to know it's there, and then if you're like, okay, is there an operation on the set? Like, I want to do this thing. Let me go see if there's an operation that does that. The reason that set is often useful, so I mean, of course, if you have a collection of elements and you don't care about the order, then you can put them in a set. It's also useful for doing things. So actually, let's just do it right now. If we go back, this part right here, so the last part of unique words, so remember we were trying to keep only identical, or like only unique words, right? And so we wanted to get rid of duplicates. And so the way we did that is we first sorted the list, and then we grouped them by, you know, words that were the same, and then we only took the first word of each group. A different way we could do that is if you just take all the words and you throw them all into a set, right? Sets don't have duplicates. And so it'll automatically kind of get rid of the duplicates while it's inserting them. And then you just convert the set back to a list. And when you do that, like it's actually going to end up doing the same thing as this. You'll get them back in sorted order because the elements in a set are stored in sorted order. But it's just a different way to do it. So here's we can also get rid of duplicates using Data.Set. So if I say unique words prime, and actually, okay, look, we got it. That was weird. So if I just import Data.Set, the problem is that it's got a bunch of, so for example, like here's a function called full-R that works on sets. There's a function called map that works on sets, right? And so if we just import it, all those, there's a whole bunch of names in here that would clash with standard names of things that work on lists or whatever. But it's designed this way on purpose because it would be kind of annoying to call this like, you know, map set and full-R set. And, so what you're expected to do is do something like this. I don't know if we've seen this before. Maybe you have. But this just means, hey, we're importing this library, but we're gonna call it S, and everything that's in there you're gonna have to refer to as S dot whatever, which just helps disambiguate. So now we can't just say map, we would have to say S dot map, and then it knows to get the map from the set module. So let's copy paste this, but we're gonna get rid of, we're gonna change this part. So all we have to do now is we're gonna say S dot from list. Right, so that takes a list of things and converts it into a set, and then we just convert back S dot to list. So just converting to a list and back will sort and get rid of duplicates for us. And it's just as efficient as, you know, whatever this would have done. Well, this sorting takes, if you have a list of length n, sorting takes n log n time, and then grouping takes linear time. It just goes through, it just scans through and groups things, and then doing this also takes linear time. So basically, the whole thing takes n log n. But this also does, because converting a list to a set also takes n log n time, because inserting into a set is going to take a long time, because it's a balanced tree. And then converting back to a list just takes linear time. So really, it's kind of doing the same thing. It takes the same amount of time, but maybe it's nicer to write it this way. So we could. Okay. Let's now look at Data.Map. So you've also seen Data.Map before, I think, if, like on one of the modules where you were supposed to. I think there's a few different modules where I've said, hey, you should use a map for this. Like if we're representing like the context in the land calculus, right? We would have a map that maps variable names to their type. So this is also based on balanced binary trees. And actually, okay, so this, we really want to look at data.map.lazy. There's data.map.lazy and data.map.strict. It's just like the strict can be, I don't know, depends on what you want, but we'll just have to put it here. Right, so this just represents, dictionaries, or what you would call maps in Java. Still really. There's also this special int map, which is specifically if your keys are ints, but we'll just use the generic map. And it also has actually a better way to do this. Well, this just gives us an overview of like all the stuff that's in here, right? So we can build maps from lists, we can insert, we can delete or update, we can look up, we can combine maps using union, difference, intersection, blah, blah, blah. We can map, we can fold, convert to list. So a lot of stuff we can do. So let's just look, for example, to construct one. So for example, one way you can construct a map using this from list function, you actually give it a list of pairs of keys and values, and it'll build the map for you. Or you could build it kind of one by one by if you just start with an empty map and you just keep calling insert, right? Insert, you give it a key and a value and a map, it gives you the map. There's also this, and I think we might end up using this later, so I'm going to highlight it now. Or actually, maybe not this one. Well, so what insert does, what does insert do if the key already exists? It just replaces it, right? So if you say, insert key k with this value and a map, it's just going to replace any value that was there with that same key previously. But maybe you don't want that, right? So here's insert with. And insert with says, okay, additionally, we're going to take a function of type a to a to a. And that says, basically, if you have two a values, how do you combine them? So if there was already an a value for that key, and you're now trying to insert this new a value, use this function to combine those two values to get you, the new value for the key. For example, if you were trying to count how many times some things occur, right, you could just say insert, the value 1 for this key, but you could say, but if there's already a value there, you should add them, and then it'll just like, every time you insert 1, it's adding 1 to the value that's in the map. But if it wasn't there, it would just put a 1 in, to start. And I think there's actually, let's see, yeah, so there's actually also a version of from list. So from list takes a list of pairs of keys and values, but if the same key occurs multiple times, like the later ones will just override the previous ones, or maybe earlier ones override later ones. I don't know, it's only going to keep one of them. So there's also a version, just like that insert with we saw, called from list with, that says, okay, take this list of pairs and turn it into a map, but if you see multiple pairs with the same key, then you should use this function to combine their values. Okay. There's lots of other things in here. For example, so there's a lot of these like with ones, right, that have the same idea. So union combines two maps, but again, if they share same keys, one of them is just going to override the other one. But union with says, okay, if these maps share a key, we're going to combine the values using this function. Also, union with key that even tells you, okay, you get to know what the key is in order to decide how to combine them. Lots of different functions here. So, all right, let's do some more examples. So let's start with given a list of words. produce a list something like, dog, pie, because those are the words that occur more than once. Right? Makes sense? So we don't want to do something like unique words, where if we just like get rid of duplicates, that's the wrong thing to do, because then at that point we can't tell which ones had duplicates or not. So kind of what we want to do is we want to count how many times each word occurs, and then we can do like a filter to only keep the ones that have a count of more than one. And then once we do that, we can get rid of the counts, right? So plan. So one is count how many times each word occurs, and then two is a filter to keep only words that occur times. Okay. So I claim a really nice way to count how many times each word occurs. So, well, let me actually back up a little bit. What kind of data structure might we use to represent the words and how many times each one occurs? Map. Exactly. A map would be really good because each word can be a key, and the value associated with the word is the number of times it occurs. So let's go back to map and think about how we could do this. So we could, of course, write an explicitly recursive function that goes through this, the pattern matches in this list, and goes through one element at a time, and kind of keeps track of a map, and every time that we see the next thing in the list, we insert it into the map. We could do that, but again, we don't want to do that. Is there a way that we can kind of just do it all at once? Just say, take this whole list and build a map with counts. And yes, we can. So this function is actually a really good way to do that. Well, we don't have a list of pairs, right? We just have a list of the keys. But each word counts once. So what I'm proposing is we first make a list of pairs where each word is paired with the number 1. Okay? And then we call from list with, and the combining function that we give it is addition. We just say, look, if you see the same key again, you should just add whatever values are associated with it. So, one of the values is going to be 1, and the other one might be, well, we've already seen 6 of this, and so it's going to add them and get 7. What should we call this? So this takes a list of string, and gives a list of string. So the first thing we're going to do is we need to, so actually, I guess we'll break this down, right? This is like 1A is pair every word with 1, a count of 1. And then 1B is use Data.Map from list with to map of counts. Okay? All right, so how do we do 1A? How do we pair every word in a list with a count of 1? Ideas? we could define a helper function, I guess. Just right away. Does this make sense? You had a look on your face like you were skeptical. So.
Yeah, I think I might be. Oh, that's a 1. Okay, so number
yeah.
1. Okay.
So that's number 1. Yeah, so it's going to take. If we had a list like, you know, hi, dog, cat, dog, whatever, we could now get a list that looks like hi, comma 1, and dog, comma 1, and cat, comma 1.
So it end up making a list of pairs
Yes.
instead of a list of the string.
Correct. Right. And you can see, I don't know if you can, it's a little small, but it's telling us now, this whole here, like the rest of what we have to do, it's now saying you need to turn a list of pairs of string integer into a list of strings. Okay, we can also, just for fun, so, right, map, comma 1, instead of, if we turn on, if we turn on the language extension, it's like language, typical sections. It's kind of like comma isn't actually an operator like plus, it's just special built-in syntax, but it's kind of like in parallel to the way we can say parentheses +1, which is the function that like does something +1. Haskell also has this syntax comma 1, which is the function that takes a thing and puts it in a pair with 1. So, we don't have, I'm not going to change this one up here. Just saying. You can even make it slightly more concise if you want to enable that language. Okay, so now we need to say, we need to import Data.Map. So import qualified. Same thing with importing it qualified because it has a bunch of functions that would clash with other standard functions. So we need to say, we're going to say m dot from list with plus. Right, because m dot from list with, it needs a function that says how to combine 2 values, and then it takes a list of pairs and it gives us back a map. And so this map will output that list of pairs, and so it'll take that and turn it into a map. And so now if we look at this whole, it's telling us, yeah, now we have a map string integer. So a map from strings to integers, and we need to turn that into a list of strings. Okay. So what should we do now? Yeah.
Is it plus and then from list with, or is it just?
No, plus is for concatenating lists together.
Oh, right. Okay.
Right. We're literally just what the plus is doing is each word is paired with a number, and we're saying how to combine those numbers if we see multiple copies of the same word. So we're just gonna add up those ones, and that's what will give us the count. If we just said from list without the with plus, then it would just, every time it saw the same word, it would just override the previous one, so we would just end up with all ones. We want to, instead of just like overriding each thing, we're accumulating the information. You know, and like, it wouldn't have to be 1, so if for some reason you already had, you know, each word paired with some number, but not only 1, like, you know, this is paired with 2, 5, right? This would still work, and it would just add up all the numbers associated to a specific word. It would add up all the numbers associated to it, and you would get that one number back. Or you could do from list with times, or you could do, I don't know, whatever. Like maybe each word is paired with a probability, and you like multiply it. I don't know. Okay. So, any ideas how we might do the next step? We need to filter and only keep words that occur multiple times.
greater than 1, but we don't need to filter the keys in the map, we need to filter the values.
Right. Yeah, so let's see what map provides in terms of filtering. We can filter maps. Is that what we want? Yes, it is, right? So this predicate is on A, which is the value.
Yeah, so that,
type. So that's actually what we want to work. So this filter function will filter on values. There's also a version of filter that takes the key and the value, and you can use both to decide whether you want to keep it or not. There's also restrict keys, that if you have like a set of keys and you're like, I only want to keep these keys and throw away all the other ones, you can do that. So there's a bunch of different ways that we can kind of filter. There's even a partition, right? So this partition gives you the map of all the things that do satisfy the predicate and the map of all the things that don't. Wow, nice. Well, all right, whatever. We just want to filter. So I'll say m dot filter greater than 1. Is that what you want? That's what you said.
yeah, that will give you a map of keys to values where the value is greater than 1.
Yep.
So then you have to just pull those words out.
Yeah, so now we just, at this point, we actually don't care anymore about the counts anymore. So we just want to pull out all of the keys. So let's see how we do that. So at this point, I don't know, maybe actually, instead of looking in the documentation, I'm going to do just to illustrate, I'm going to do a Google search for a function that takes a map KA and gives us like a list of keys. So there you go, that works. You do have to make sure that it's in the right package. So like here's one called keys, but that is in Data.Map, which is from the hashmap package. But this is from containers. This is in Data.Map. So let's say keys. Let's try it out. Works. Cool. Any questions about that? What are thoughts?
That's sorted as well.
It does actually sort it as well because of the map, Data.Map is implemented using like a balanced binary search tree. That's how you can efficiently look up keys because it's in a search tree, so it can go left, right, it can find it in long time. So when you get out the list of all the keys or whatever, it just like kind of traverses the tree from left to right, so you get them and sort it for you. And I think the documentation says that. You can actually rely on that. It's not just like, well, this is the order that happens to be right now, but don't rely on that because maybe tomorrow it'll change. No, I think it's pretty nuts. Yeah. Return all keys to the map in ascending order. Yeah. So it guarantees. The subject to list fusion thing. So we were talking about the other day. Now we're talking about how, in theory, you look at this and you think like, oh, in between each part of the pipeline, it has to produce some intermediate list that's then going to get used again, and then it's going to produce another intermediate thing. But then actually Haskell works really hard to get rid of all those intermediate data structures. And so this subject to the list fusion is what is the technical term for that idea of kind of getting rid of intermediate lists. And so I think what this is saying is, if you call keys and then do something else with the resulting list, it can actually optimize that and get rid of that intermediate list.
So a set has to always be in some order? It can't be, what if you wanted an out of order set for some reason?
What do you mean an out of order set?
Um, like for the example we just did, it gave all the results in order. I
Yeah.
guess that was because of keys.
Right.
But since a set is like a binary search tree, I guess it can't be out of order, like it's always
Right.
in some order.
It's always in some order, right?
Okay.
That's how it gets your login efficiency, because if it didn't know what any order from at all, then it would just have to do like a linear search or something. It would just be. Now, so you might ask, maybe this is what you're trying to ask, what if I have some keys that kind of don't have an ordering? How could I put them in a set? Well, the answer is you can just well, okay. There's actually two different ways that question could be asked. One is, what if I have a type that could be ordered but isn't? Like it doesn't actually have an ordering defined on it, but you could. Well, in that case, you can just define some ordering. It doesn't even really matter what the ordering is. It doesn't matter if it kind of makes any sense. As long as it's a valid ordering, then set will be efficient. So that's one answer. Now you might ask, well, okay, but what about if I want to store like, a set of functions, and like there's no way to decide, which function is less than another function? Well, you can't do that. And so you would have to find some other way to, instead of storing functions, maybe you store some kind of codes that represent the functions, and then you can later interpret the codes and give you the functions. But yeah. But it's really no different than any other language. So like if you use a tree map in Java, you can only use it with key types that implement comparable. Right? If you use a hash map, well, everything by default has like a hash code method, but not everything has a sensible one. So you still have to kind of make sure that hashing works. Yeah. Yeah, but I guess the point is that the order doesn't really have to it doesn't have to mean anything. As long as there's some ordering, then you can use it. So. Cool. Any other big questions? Other questions? I will point out a different thing we could have done, and I'm not even sure. I don't think one is necessarily better. I'm just pointing out an alternative. After we did from list with plus, at that point we could have converted it back to a list of pairs, and there's a function to do that. And then we could have filtered that list of pairs and said, okay, only keep things where the second element of the pair is greater than 1. And then we could say, now just throw away the second elements of all the pairs. That would work too. And I think it would be pretty much the same in terms of efficiency. I think I actually like this better, honestly, because map gives us a function specifically for filtering on the value, whereas if we converted it to a list of pairs first, we'd have to it would be a little bit more verbose to say, oh, we want to compare them, we want to filter, but we only want to look at the second element of these pairs and see if that thing is greater than 1. So it would be a little bit more verbose. Let's see, I had another example of something I wanted to do, which is what? Right. So here's another example. Given a list of things, find the element that represents the greatest increase over the previous element. So for example, say, okay, 1 to 7 is an increase of 6, 7 to 8 is an increase of 1, 8 to 19 is an increase of 11. So I think this 8 to 19 is the biggest increase, right? And so I wanted to return 19. Because 19 minus 8 equals 11 is the biggest. Does that make sense what I wanted to do? Again, kind of a contrived example, but I don't know, maybe you have some set of data and you're looking for, you want to see like when is the point in the data at which like it jumped up the most or something. It's a reasonable thing you might want to do. I mean, so any ideas how we might do this, or what might be some pieces that we would use to do this? And of course, I know that like you're not super familiar with the Haskell standard library, so also you could have an idea. It's like I'm kind of thinking I might want to do this. Like, is there a function to do that? And then we can look it up and see if there's a function. Yeah.
You could start possibly by making just a list of pairs where you keep the previous as the starting. After you get past the first one, you keep the previous as the next
So
start.
like pairs of consecutive elements, like 1, 7, 7, 8, 8, 19, like that. Yeah. So I like that. So a list of consecutive pairs. So 1, 7, 7, 8. Any ideas how we might do that? Again, we don't want to write our own explicitly recursive function. So we could do what you just said, and we could go through it one by one. We would have an extra parameter, which is the previous number, and then we could, when we see the next thing in the list, we just like output that pair, and then we call it recursively. But we don't want to do that. Any ideas of how we might produce a list of consecutive pairs like that? Kind of all in one go. So let me show you a function from the standard library that might be helpful here, that maybe we haven't looked at before. So zip, if you give it two lists, it kind of zips them together and it pairs up the first element and then pairs up the second element and pairs up the third element. So any ideas how we might be able to use this to do that thing we're trying to do?
Zip. Like, I guess you would want to give it the example list and not a list without the first element.
Exactly. Right. Which we can do by saying tail. Yeah, so if I zip this list with its tail, so if I take the tail, that's the list that starts with 7. Right? When I zip those together, I'm going to get each pair of consecutive things. So I can do this using zip, x's, and something like zip x's and tail x's. So just as an example, where if I was zip, let x's equal 6, 9. If I say zip x's and tail x's, that's that. And it automatically handles, right, because one of these x's is going to be longer than tail x's. Tail x's is going to be one shorter. And so when it gets to that last element, 9, there's nothing to pair it with. And it just, I don't know if you noticed when we were looking at the documentation for zip, but it just cuts it off there. It just ignores anything that's too long. So that's Perfect. Okay, then what? Yeah.
Could you use like a map
Mhm.
and subtract like the second minus first?
Yeah. So map, uh, map. So use a map to turn each pair of A, B into B minus A. Is that what you mean? And so I guess, we could, that would be like map, well, and when I say turn this into that, I mean, literally just write a lambda that says, lambda A, B minus A. Yeah. And actually, there is a function, subtract, yeah. So there's a standard function subtract that is like minus but flipped. So let's say subtract. I guess also if we zipped these in the other order, then we could just say normal minus, right? Like there's no particular reason they have to be in the order like 1, 7, 7, 8. It could be 7, 1, 8, 7. So I don't know. Let's do that. So if we say like, oh, whatever. There's a lot of ways you can do this, right? Okay. So now that would give us a list of the differences, right? Or a list of the increases. So we have like 6 and then 1 and then 11. Okay. And obviously we're looking for the biggest thing in that list, which we could do just by saying maximum. The problem, right, is that we don't want the maximum value. We want kind of the value that came after that increase. So if I just say, okay, at this point just find the maximum, I would have the number 11, but I don't have a way to like figure out what number up there went with 11 anymore. So any ideas how would I can't just take the maximum of this list. I need to do something else. Any ideas?
We get the index of the maximum and evaluate.
Yes, that's one thing we can do. Let's see, is it possible to find the index of the maximum? So we want something like, well, max index, okay, but that's like for vectors. So I don't actually think in the standard library I don't think there's a nice function that gives us the maximum, the index of the maximum. We can find the maximum value. And anyway, I don't like using indices, because it's easy to like be off by 1 or whatever, so. Can we think of another way to do it that does not require using an index? Yeah.
If we, when we convert it to this list, if we convert it into like a pair with, like turning a pair A, B into a pair B, comma, B minus A.
I like that. So what you're suggesting is instead of just taking each pair and then just turning it into a single number, which is the increase, let's turn it into a pair, which is the increase and the number that's at the end of that increase. And then we can just find the pair with the biggest increase value, and then we'll get whatever value is attached to it. Yeah, and we can either do that, so in this case, yeah, we should just turn it into a pair here. We could also, if we kind of got this list of maximums from somewhere else, and then we had the original list, or the list of increases, we could like zip them together in some appropriate way to make those pairs as well. So it would be the increase pair with value you can't say map subtract anymore, I guess. And then we'll find the pair with the biggest first value. And then just, okay. All right, so let's, we've got a couple minutes, let's just write quick. So, I don't know what to name it. Biggest increase makes it sound like it's going to return the actual increase. But I don't know what else to call it. So we're going to first, and actually I can't
The list,
just do it.
right?
What was that?
You gotta have the list this time, right? Or do you need to?
Say that again?
You have to have the list this time, or not?
What do you mean?
The, like, actual name of the list?
Yeah, we do, because I can't, like, because I have to use it twice here, right? I can't just make it a, just a simple pipeline, yeah, that's okay. We can still, at this point, we could say like, so the dollar sign is just like function application, but it lets you avoid parentheses sometimes. But we can like put, you know, some functions over here that we're just gonna apply to that thing, so we can still kind of this way. So once I do that zipping, then I'm going to say map A, B, to B minus A, B. And then we're going to say maximum by. So maximum just finds the biggest thing. Maximum by is going to find, and actually, you know what? Maybe even just normal maximum would work, because the way that pairs with, so the way you compare two pairs is by first comparing their first element, and then if it's a tie, you compare their second element. So why is it doing? Oh, because I haven't. And then that will give us an actual pair, and then we can just say just return the second element. Let's just try it. All right. Have a good weekend. See y'all Monday.
One thing I thought about Jordy on that first part is, could you potentially double every element after the first one? And then just do a regular walkthrough of pairs? I don't know if there's an easy, maybe there's a function that does that, but give like a regular, like a list of pairs from that.
Yeah, you could.
I just thought of that after reading.
Yeah, that's an interesting idea. So there is like a, I don't know, there's
Like a duplicate of everything after the first one.
list dot split, and you can say like, oh, it doesn't have that. There's like a function called chunks of that'll like, I'm say, oh, give me like 3 at a time, and goes take these 3.
Yeah, okay.
But actually, but doing that thing in the first place, where you double every element other than the first, I mean, I could think of ways to do it. I don't know.
It sounded more difficult
none of
than
them
what
are
we did.
particularly nice.
Yeah, it sounded more difficult than we did. I just
Yeah.
thought it might be.
Yep. Yeah. There's lots of ways to do it.